Alright, in this video, we study some of the basic properties of vectors, actually the set of vectors. And based on those properties, we can actually define more abstract or general vector space. So let's start. So we have seen a vector like this, x1, x2, and so on, xn, which is an element of this n-dimensional space. In this case, each of these elements or components is a real number. However, we can define similar thing for complex numbers. So instead of real numbers, we can use complex numbers. So in that case, each of these elements will become a complex number. And similarly, we can also define a vector where the elements are rational numbers. Okay, so the point is we can define a vector for any field. So we know that the set of real numbers is a field, set of complex numbers is a field, and set of rational numbers is a field. So we can define a vector for based on any of these fields. So just give a general field and write it as a K. So K is a set where addition and multiplications are defined, and those addition and multiplication satisfy some basic properties of the field that are closure for addition and multiplication, and commutativity, associativity for both addition and multiplication, and distributive law. So multiplication distributes over addition. So if those conditions are met, then that set is a field. So for any field, we can define a vector. So just for the sake of generality, we write something like this. So depending on the context, this K can mean real number or complex number or rational number or any other fields. So in that case, addition is just defined similarly, and xn plus y1, y2, and so on, and yn is equal to x1 plus y1, x2 plus y2, and so on, and xn plus yn. And each of these x1, x2, and y1, y2, and so on are elements of this field K. And the scalar product is defined for a scalar that is an element of the field K. So in that case, lambda times x1, x2, and so on is just this. So formally, it's just the same as before, where we define vectors for real numbers, real elements. So the set of vectors, of course, that is a set of these tuples together with addition and scalar multiplication. We call it a vector space. Okay, and over some field, the field K. So this K can be real number, complex number, and so on. So vector space is a set of vectors. Of course, I mean, vectors can be defined as elements of a vector space. So in that case, we cannot say vector space is made of vectors. I mean, that's, we use vectors to define a vector space, but we use vector space to define vectors. So it's a circular argument. So that's not a good thing. So in that case, in our case, we first define vectors as such elements with addition and scalar multiplication, and as a set of those vectors, we define the vector space. Okay, so as such, we can derive some properties of the vector space in general. based on addition and scalar multiplication. And after that, if we can find a set with addition and something like scalar multiplication that satisfy all the properties of the vector space, then we can define the elements of that set as vectors. This may sound a little bit abstract, so let's see step by step. Okay, so let V be a vector space. So this is a set of vectors where addition and scalar multiplication are defined. And now we have the following property. It's a vector space over some field, over K. So K is a field. Anyway, so here are the properties. For all vectors U and V in this set, vector space, we have U plus V is also an element of V, the vector space. So this is called the closure condition. Just like we saw in the case for field, addition and multiplication in the field. So these fields are closed under addition, right? Just like that, we have a vector space that is closed under addition. So it's called closure condition, closure of addition. And 2, for all vectors, pairs of vectors, U and V, in the vector space, we have U plus V is equal to V plus U. So this is, of course, commutativity, just like fields. Commutativity. Okay. And 3, for all triples of vectors U, V, W, so these are vectors, we have associativity. That is, first we add U and V, then add W, then that is equal to, we first add V and W, then add U. Okay, so this is associativity. We say vector addition is associative. TVT. Okay. And 4, there exists a special element called 0 in this vector space, such that for all vectors U in V, we have U plus 0 plus U is equal to U. So adding 0 doesn't change the vector U. So this special element is called 0 vector, so existence of 0 vector. Or you can say additive identity vector. And 5, for any vector U, there exists a special vector V such that U plus V is the 0 vector. And such V is actually written as negative U. Okay, so this one is usually written as negative U, and it's called the additive inverse of the vector U. So in that case, we write U plus negative U, but we often abbreviate as U minus U. Okay, so this is just a shorthand notation for this expression, and that should be equal to the 0 vector. So this is also similar to the case of fields. So in the case of field, we always had additive inverse of any element. Just like that, we have additive inverse for any vector in the vector space. Okay, next about scalar multiplication. And for any scalar that is an element of K, K is a field, let's say it's lambda. And for all elements u in the vector, we have the scalar product multiplication. Lambda times u is also an element of V, the vector space. So again, this is a closure condition, but this time it's for scalar multiplication. So the vector space is closed under scalar multiplication. And 7. And for any vector u, and for any lambda and mu that are scalars, elements of the field, we have this lambda plus mu times u is lambda u plus mu u. So this is a distributive law of scalar multiplication. So this multiplication distributes. Okay, distributive law. So in this case, we first add two scalars and multiply that to a vector, and the result is the sum of two scalar multiplications of vectors. And next, similarly, for all pairs of vectors, u and v, so u and v are vectors, and for any scalar k, lambda, scalar lambda in k, we have lambda times u plus v is equal to lambda u plus lambda v. So this is another type of the distributive law. So we first add two vectors and then multiply by a scalar, and the result is the sum of scalar multiplication. And next, for any element of the vector space, 1 times u is equal to u. Okay, and this 1 here is not a vector, by the way. So this 1 is the multiplicative identity of the field K. So according to the axioms of the field, it's guaranteed that there exists a multiplicative identity, which is usually called 1. Okay, so the existence of this element is guaranteed because we are assuming K is a field. So anyway, so if we multiply any vector by 1, then the result is that vector unchanged. And the next, and finally, for any two scalars, lambda and mu in the field K, and for any vector u, we have this associativity of scalar multiplication. We first multiply lambda and mu, which is possible because K is a field. And the result is equal to lambda times mu times u. So this means, the right-hand side means we first multiply the vector u by scalar mu, and then to that result we multiply, by the way, that result is a vector, according to the closure condition. And then to that result, we multiply the scalar lambda. So this is equal to this. So we can say scalar multiplication is associative. So this is another kind of associativity. Vt. I think all these properties are quite obvious, so I don't give a rigorous proof for that, and you should try that instead. But instead of proving, I will just show you some examples. For example, let's say we have two-dimensional vectors, say a, b, and c, d, in two-dimensional real space. Okay, so these two vectors are elements of this space, this vector space, and if we add them according to the definition of addition, we have A plus C and B plus D, which is, A plus C is, of course, is a real number, and B plus D is a real number. Therefore, this is an element of this two-dimensional real space. It's obvious, right? So addition, vector addition is consistent. I mean, if we add two vectors, it doesn't go beyond this space. It stays in this space. In this sense, this vector space is closed under addition. And the same thing applies for scalar multiplication. So if lambda is a real number and A and B are real numbers, the result of this scalar multiplication is lambda A and lambda B, which is, of course, an element of this two-dimensional space. So this space is closed under scalar multiplication. And what about this additive identity, this thing? So what is the zero element of the vector space? And maybe you can guess, and that is, in the case of two-dimensional space, it's 0, 0, right? If we add 0, 0 to any two-dimensional vector, the result is 0 plus A and 0 plus B, and that is equal to A plus B. So adding this element doesn't change this vector, right? This is equal to this. So the vector consisting only of zero element of the field K is the zero vector. And if we have u1 and u2 as a vector, then its additive inverse is, let's say this is u, then its additive inverse, negative u, written as negative u, is negative u1 and negative u2. This can be checked by adding them. U plus negative u is equal to u1, u2 plus negative u1, negative u2. If we add them, we have u1 minus u1 and u2 minus u2. That is 0, 0, which is the additive inverse. By the way, as you can see from this, this additive inverse can be written as negative 1, which is a scalar, times u, right? So in this way, you should check all these properties for example, two-dimensional real space or real two-dimensional space. Now, let's assume that you have examined all of these properties for example, real two-dimensional space, vector space. And so we define vectors first, like A, B, and then for these and scalar multiplication and addition with this. And we derive these properties, or 10 properties, right? Now, we reverse this argument. That is, we first specify some set, okay, any set, that comes with an addition between elements of this set, and scalar multiplication somehow defined. And of course, in order to define scalar multiplication, we have to specify the set of scalars that which is a field. Okay, scalars are elements of this field K. Then any set equipped with addition and scalar multiplication with elements of K, a field K, that satisfies all these properties, all these 10 properties, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 properties, is called a vector space. Okay, in this way, we do not explicitly specify this is made of an ordered set of numbers or tuples of numbers, right? This can be any set, as long as addition and scalar multiplications are defined and these operations satisfy the above 10 properties. Then that set is called a vector space. So actually, these 10 properties serve as the axioms of the vector space. So just like we define a field in general, in the way that it's a set with addition and multiplication that satisfy some axioms. So any such sets are called fields. And just like that, we define a vector space as this. So any set equipped with addition and scalar multiplication, where scalars are elements of a field K, then that set is called a vector space over K. Over K. So by defining vector spaces in this way, we can regard many things that are not just ordered tuples of numbers as vectors. For example, a set of functions defined on some closed interval can be regarded as a vector space of some sort. And that allows us to study many huge variety of things as a vector space in general. So once we can prove some general properties of a vector space, then that properties can be applied to any concrete or specific vector spaces, not just vector space of real numbers. Okay, that's all for this video. See you later.